Hi friends, so we are into our 12th and last module of this course, Risk Conscious Operation Management of Complex Engineering System. And this lecture is on application of artificial intelligence to operational ecosystem. It could be management, it could be operation, it could be services. In previous lecture, we saw how we build the subject, and then finally we gave an example of operator support system. And then now let us see something for which is directly related to maintenance. So this is prognostics, health and health management, a systems approach. So through this lecture, I am enhancing the scope of PHM to a system level. And how we do that, you will see in the lecture. Okay. So actually PHM as a subject, though it is related to maintenance, it has got a reliability connotation, because we say the reliability is nothing but a probability of a component for failure free operation for a given period of time under a stated condition. That's how we define, and mathematically we express it like RT, that is reliability as a function of time, is equal to probability. Capital T is a random variable, so that means uncertainty is a part of this statement, and it should be more than 2. So that means the time for failure should be more than the mission time. That means in other word, component should work for its mission time, and this applies with the condition C1, C2, C3. It could be temperature, it could be humidity, it could be mechanical load, it could be lab environment. So whenever people will buy with a item with a reliability, they will know the background. These are the things they have be condition. They have be, if you operate in a degraded condition, reliability could be poor. So it is a statement complete in itself to the extent required for a person who is buying a component. Okay. Now, as I told, C1, C2, C3 are conditions. Capital T is a random variable, and small t is a mission time. Okay. The problem, I am making a very important point here. The problem with the probabilistic notion, we say probability of failure, is that even though time is a function, we don't talk about the instant of failure. We talk about the probability of failure. Now, this is something, even though at system level it gives assurance for broad characteristic of the component or quality of the component, but it does not talk about the instant of failure. So we have this PHM, prognostics and health management. Its a major output is remaining useful life of a component, but the important thing is PHM is a technology wherein we put sensor on the subject that we are monitoring. It could be system, it could be individual component, or it could be even human. Actually, this prognostics and health management, this whole field has been inspired from the healthcare sector. So what we do basically is we put sensors, and these sensors are monitored. And the moment there is a change in signature of this sensor signal or precursor, we can call it, we keep tracking its degradation level. Okay. And while having a degradation level statement, we are actually seeing what is the remaining useful life of the component. Why we are able to do that? Because these statements come from a lot of testing, measurements, and then characteristic of individual component to some extent based on the physics of failure of the component, or it is the data driven trick. Like say you have certain component, you put n component under a test. Now what you get in probabilistics domain, you get a mean time to failure. So here the next to the mean time to failure, uncertainty is reduced by tracking the degradation, and we know how far we are away from the failure. And this particular thing is very useful in industrial environment, R&D environment, or even societal environment, because we know this component is not going to fail in next 25 days, because there is no sign of degradation. That means I can plan maintenance of this component next 30 days or whatever period has been coming on. But the moment degradation start, then we have to be clear. Okay, now we have to take it. It will operate, because we know we can read the trend. So if the trend is very feeble, it can give us 1 month, and that's how we are able to. In plant, there is a term called allowable outage time. That means if a component fail, plant has to be shut down or derated. Now for certain components, if this happens, of course, a lot of redundancy is built and we don't depend on the one component. But then allowable outage time, let us say one equipment went out of the order during plant operation. But our plant specification says if the equipment fail, though you have redundancy and diversity and all that, its allowable outage time is 8 hours. If 8 hours you are not able to repair it, even with plant operation is allowed. If you are not able to repair it, plant should be shut down. Don't you think it is a harsh statement? But then safety operates with a conservative principles. But suppose now we have a tracking mechanism, and now we can say when the degradation level is goes to a level where it affects the safety. I'll show you how this gets reflected into the prognostic metrics. So, how to define the prognostic metrics? Having understood how its mechanism, how it operates, prognostics and health management deals with the evaluation of remaining useful life of the component. Remaining useful life, it can be at the component, it can be there at the plant level also. And that's how I am talking a system level approach. And just to give you a feel of it, we have done projects on this, and we have given a way out for plant life extension. Imagine if somebody tells you the plant is 30 years old, now you have to perform the aging studies, otherwise you have to shut down. And then you have an opportunity here to implement prognostics and pre-RA metrics, and then you get a extension for 10 years. It is not imagination. It is a real thing which has happened for the plant. You are talking about the component. So prognostics and health management is a case how closely you are able to monitor. One step before this RUL or PHM is a condition monitoring. You know that condition monitoring, you just put the sensor, monitor the sensor on the panel, and then like it happens in our healthcare system, when the bits goes higher and all, then you say, okay, you need the treatment and you have to take rest, something like that. So here also, based on the data, it keeps updating you about the status of the plant, and we have only constraint is catastrophic failures are not covered in this. Sudden failures, would a brittle pipe, okay, carbon steel pipe, or cast iron pipe, it will not give any signal before failure. Or for that matter, any plastic item which is built, it could be casing, anything, it may not give any signal before the failure. So we are not considering catastrophic failure, we are considering failure which propagate based on the degradation mechanism, and which gives sign of their degradation levels. So now we have understood the difference between reliability. So we can say PHM is a higher and advanced version of reliability, because we don't get the probability. We are not limiting ourselves to probability, but we are trying to determine the instant of failure with some uncertainty, because data is always have a randomness and their uncertainty, but that uncertainty should be such that we are able to absorb the advantages in our plant operation and maintenance. Okay. Now traditional approach, I told you that we used to do periodic testing, then general surveillance and all, and there were so many techniques are there to ensure that the component is operational characteristic, operating characteristics are kept well as far as the quality is concerned. Now requirement of prediction, as I told you, has come because the precursor signature that is available to us, it helps us in understanding the incipient failure. So if I have to explain through this figure, nuclear plant, there is some component which is being monitored online. So we are tracking the precursor parameter signal, and then we perform the prognostics. So initially it was sort of like horizontal, then it deviated, and then it here, and then the failure occurs at this point. Okay, so this is our prediction that the failure will occur at this time, and I think we had an opportunity to observe the deviation, and this particular time from here to here, it could be it is a qualitative representation. It could be somewhere from 5 to 10 minutes to even 5 to 10 days, or 3 to 4 months, or it could be anything. So that means this warning signal which was available at this point of time prepared us to track this very closely, and record these things, and then with a more magnification, this thing, and then prepare for maintenance or corrective mechanism. Now this prediction will occur not as a line or as a point, but it will occur as a like, if we can explain it better, by a normal distribution. That means the early failure or late failure. So, and this is the mean failure. So basically this line has been drawn for the mean failure, but I have information about our lower bound, upper bound, and for my safety, I will take the upper bound, that earlier this thing. So that could be, you can say, conservative. That means degradation has taken up to this level. I will assume that. So it is up to us how conservative you want to go, and the applications are infinite, and especially as part of risk informed risk-based approach, risk in-service inspection, which we do periodically. We do a periodic checking on a component. We do after 1 year, after 4 years, after 3 years, depends on the severity and the component's safety significance. So this is how a simple schematic to explain you the prognostics and health management of a component. We are going in this lecture one stage ahead. I have one paper in this thing, in PHM Society from NASA. So you can go through that paper. I have given the reference here, how it can be done at the system level, how structures can be identified based on various criteria. But the thing is that this PHM, to a large extent, even today, it is in R&D domain, and few elite industries like aviation, then space, and to some extent, I don't know, a few applications you will find about in nuclear plants also in some way or the other, and then for dams and this thing, in the form of health monitoring system, it has been available. It was available because in dam you have to see the structural integrity in spatial domain and in time domain also, and that if any indication is there, immediate repair has to be effected. So that's how. But I said challenges. What are the challenges? It is because of if we talk at the material level, that is at physics of failure level, then a lot of testing experiments have to be and then based on how crack propagates, that itself is a big this thing, and what is the critical crack length, this kind of thing in mechanical and all, they are there. And once we have enough confidence about this, in real time condition, lab environment, all these things they do exist, but with so much of uncertainty, so physics based method, then data driven method. For example, if I have been operating a bearing and there are similar machine, like 100 machines are there, they have been operating for 20 years, let us say we have a huge amount of data. So PHM has got two options. One is, I'll be coming to those slides. data driven approach and physics of failure approach. And with that, I think at least for remaining useful life of mechanical components and electronics, I think it has progressed well actually. I was telling you system level. Why you need system level? On system level, you see. Let us accept it that PHM is a very expensive option, resource consuming option. It is not possible to install PHM system on all the components, but definitely it can be installed on life limiting component, one criteria, and second one is they are ranging very high on safety importance. So suppose through this PSA, fault tree, event tree and all, if I produce a list of component with importance measure, we have already discussed in previous lectures. So the highest importance 20% component if we take, and of course with a qualitative evaluation, we can work on those. You can get this thing confidently with 20% coverage. You will get 80% advantage. Okay. So this is very important because you have considered based on the safety significance. So systems approach helps us. It is using 3-4 more metrics to arrive at the prioritization of the component and identification of the component, and based on that PHM can be implemented. So like from risk events which are not safe, they will become important for us. Okay, and then we can rank them because this is only one event is there, and that is PIE for loss of offset power. There are 20 more initiating events are there, and then at core damage level we can prepare a list, and you can see here how summing up of this insight, unsafe side will lead us to the core damage frequency. So here you get at system level. From system also which component rates higher and all. Obviously, another characteristic is common cause failure causing events. There will be human factor, common cause failure. Human factor events will give us a opportunity to do introspection and improve the training program. Okay. Similarly, common cause failure. Normally, there are defense mechanisms available in to reduce the consequences of common cause failure like separation, distance, and so many things are there. But then still common cause failure do occur. Okay, and at international level there is an effort to develop a common cause failure program. Say for instance, nuclear energy agency, they have been working very actively on this, and maybe one document must be already in public domain. So, but that apart, what we are saying is PHM is very expensive technique, and like condition monitoring cannot be, when we cannot put condition monitoring for all the components, how we can do PHM? PHM is much more expensive, while PHM is nothing but extension of condition monitoring in a general way actually. So this systems approach is required, so that because one or two component monitoring will not help. We have to monitor a chunk of component which takes us to one stage higher level in terms of safety and reliability both. Okay, so we are talking about PHM approaches. I think I have already given the background. There are two major approaches. One is called physics of failure approach, wherein there is a system or component, system structures or component, whatever is your subject. Then you have life cycle loads that you have data about it, and then with that we do life testing, environmental testing for under high temperature, humidity, or whatever stresses that is critical to the life of a particular component. And then physics of failure model is created. That means a model that will give estimate of remaining useful life based on the parameter that we have its function of. So you got a very I would say scientific approach for giving us a remaining useful life prediction. And the other approach is, it is called PHM, our subject. So here the sensor data, we are monitoring this data, domain specific analysis. If it is a bearing, a mechanical analysis will be required because there are 4 component, inner race, outer race, ball, and then locking mechanism and all that race inside this thing. So what is damaged? we want to get that information. So it is like a component specific expertise is required. And then, as I mentioned, pre-processing of information is very required. If we put the data as it is, it will be for ANN, it will be difficult to predict the remaining useful life. And after that, extract the feature, which frequency picks up, or what is their amplitude. If there is one available, other not available, what could be the reason? If both are available, their amplitude, uncertainty in that. So this is what, and then statistical modeling is done. So when we have this approach, statistical modeling is required both, because we have to give statement of uncertainty for the RUL, and then it is fed to the machine learning algorithm. So there are vectors, and finally you get a prediction of life, the component. And I have talked about two approach. Third approach is called fusion approach, in which these two knowledge, they are to so normally also you can do it, but in fusion approach you have a strategy to use this knowledge and predict the remaining useful life. Idea is to reduce the uncertainty in the final estimate. Now we have discussed this approach, but what is the relation of probabilistic risk assessment, PHM, operator advisory systems, and how, what kind of inputs are required at plant level? What do you want? That clarity is not easy to obtain, but I am trying to explain through this simple figure that nuclear plant, if I have to discuss example, have all monitoring, surveillance, control room, procedures, method, data, and they have safety system, process system and safety system, and then the raw data is collected from the log, or from so many methods are there, but mainly it is the plant log. Data pre-processing is performed here, and then AI/ML toolbox is there, and that will give us PHM and the OPD, operator advisory system. PHM will predict our remaining useful life, and the operator advisory system will do identification of the transient and diagnostics. And these three together estimate of risk through PRA, and PRA supports here PHM also and operator advisory system also. And once you have PRA, you have risk statement, you have RUL statement, that means statement of reliability as well as risk, because we have got this information from PRA, it is built from there, and then we have identification of diagnostics. So all the three together, it provides a decision matrix, and based on the decision matrix, the action is taken and the operation is in closed loop is performed. Okay. So OPAD means operator advisory system. So now if we go further and look at it, we are trying to, now we are sort of entering into the deep learning. Okay. So in deep learning, that's we had artificial intelligence, machine learning and deep learning. So in machine learning, when we enter into the deep learning, then one of the very important step is pre-processing in deep learning. Pre-processing means present the data to the network which is understandable, which can be analyzed, systematic, and they are not vague actually. Okay. So all vagueness, outlier. So these are the processing. Generally there is exhaustive list, but I am just giving involvement of domain expert. So the moment you talk about the, of course I've been emphasizing that only mother knows the baby. So the domain expert or operating crew, they will know their component and all, how they behave, when they behave. Without involvement, the probability of success will be less actually. Selection and optimization of learning vectors, and this requires a complete knowledge of the plant, not in a very you can say skewed way, identifying those parameters based on the design documents and all that. Operating experience will be required, because so many noises are there which have to be handled, so many maintenance schedules are there, they impact the maintenance and operation. Then identification of outlier unnecessarily bring the emphasis where it is not required. So this is, though physically it might look easier, but sometimes there are outliers which are there on the negative side also, which are not seen actually, and for that we require an expert. Then normalization. If I have to use the data for input, I have to bring them at certain standard level. So, if let us say simplest normalization can be, I normalize my data between 0 and 1. Now, here ANN job has reduced, its intricate energy has been saved for handling the data from 0 to 1, and and this I have used, it works very well actually. Segregation by handling of fuzzy data. Some data they create problem, then the data point, then giving the solution. So, imprecise data, fuzzy data, they should be filtered out, and a crisp set should be submitted to the input layer. Considering the missing data, whether you do it or don't do it, you will have to face the situation of missing data, and in the context of missing data, your model should be able to predict. So, there are ways understanding the science and relationship of component through either PSA or through operational knowledge. You have to bring in this factor, that if I take the data, critical data, how my ANN performs, there are derived information. Based on that, it should be able to do it, and that's how the ANN is expected to behave, or the deep learning algorithm is expected to behave. Removing or reducing such that main precursor in terms of signal amplitude and frequency became prominent factor for anomaly detection. Okay, anomaly detection is one of the important thing. Failure and all this, they are coming later. So, basically, if you can do something at anomaly level also, you are doing a huge favor to your project in terms of success of the project. And prognostics help me deal with the evaluation of remaining useful life. This definition I think we have given in the previous slides. Okay, this slide is for everyone to see what are the ANN models, especially I think the paper I see, they are mostly on either image processing, they are on bearing life estimation, vibration signature analysis, and all that, these kind of things. So, they like feed forward and back propagation architecture I have used, and this is for transient identification, and it works very well with the sigmoid function I have discussed in my previous lecture. Then this convolution, this thing, it is very good for pre-processing and abstraction features actually. And then most promising model for sensor data vector requiring identification subcomponent bearing like inner race, outer race, ball failure, high capability of learning and prediction. And then there is another class of which is called recurrent neural network, and there are two cases, two models here, long short term memory LSTM and gated recurrent units GRU. These class of networks, they are designed for processing sequential data. And what is the problem definition? If we have vibration signature is coming in time domain, and if we want a solution, often it is required that we have to compare the previous signature with the current signature, because a decision has to be taken by ANN, and this recurrent network, they provide that opportunity, and they have retrieved something from the memory, and they provide this for comparison, and they are very effective in handling time series data actually, to be very precise. Effective handling transient data that is evolving in short time domain, or even follow up sensor data in temporal domain. Okay. This is one of the most popular algorithm autoencoders. This model is designed for time series frequency, again here also domain for anomaly. So, here it is more fitted for anomaly detection, or capturing that provides rules or incipient fault trend detections. Efficient learning for complex data set, whatever. So, and the next is GAN, generative adversarial network. I think this is one of the class which is for language interpretation and all that, machine learning, image processing, they have become very popular. And then our subject, deep learning neural network, that will be taking up next slide, pre-processing, feature extraction, having more than one hidden layer, okay, and extracting some signature from there also to understand how NN is processing it. So, that is where the deep learning model comes, and here is a simplified representation of deep learning model. You can see we had n number of vectors, training vectors, and these training vectors were not put to the NN, which in 90s people were doing it. Okay, this they were pre-processed, the methodology I told you, and feature extraction. Sometimes instead of presenting the vibration signature, we can extract the feature and present that to NN. So, lot of energy will be saved in terms of processing and removing the ambiguity, okay, or fuzziness. And these networks are fed, and as you can see, input layer, hidden layer 1, which is information is tapped here to understand the processing, hidden layer 2, and there could be n number of hidden layers. So, we have moved away from the concept of single hidden layer, and now you can have one or more than one, and then there is the output layer here. And you can see here this n vectors have been put. Instead of n vectors, we can have horizontal signature also coming in time domain, like it happens in the time series modeling. Now, this is a very important slide, because any PHM application, you should be able to evaluate it, how well it is serving the purpose or how well it has been designed. So, this is the metrics I have explained in my paper on prognostics and role of prognostics in risk-based engineering in 2012, and I think I still find it very useful. So, performance metric has to be drawn. So, you can say T is equal to time 0. I will just go to the major aspects, because this diagram is, it might take even 1 or 1.5 hour also on itself. So, now here we have this diagram. There is some epoch here where we think about this, and then what happens putting the PHM on. And the important thing here about this representation is we are giving the risk statement also. So, what is the risk to from this component, and how it is risk is increasing slowly the way it happens in the risk monitor. And the question here is allowable outage time. I gave you a hint about one component has failed when plant is operating, and the text spec says you have to shut down the plant if it is not able to repair in 8 hours. So, 8 hours is a allowable outage time for the component, and you can see here risk has been CDF has been increasing. Just I have amplified it to make it understandable or comprehensible. So, and then here one of the major metrics is the time between the predicting time, between the predicted time of incipient failure and actual component failure. So, suppose if I have done prediction at this point, mean value, okay, and the failure occurred over here. So, that means it is giving me time to recover, okay, and allowable time was here. But now suppose if the component had failed, and so that this much time would have got reduced, so for me actually, and I would not have been able to do, because failure has happened. Now consequences are there for us actually, okay. And then this A, B, C have this connotation is the time for advance recovery, and the B is safety margin. Now we got a additional margin here, B sorry, and C is basically enhanced safety, because we are able to detect it here, and then we got so much time over here, and losses were less, or risk reduction was affected. And other things are precision and accuracy as usual, they have their own condition, but you have to understand prognostic distance, time to failure, prediction, and the time at which the component has failed. The time gap between these two events is called prognostic distance. And then we have a case study on filter. It is just for the, because specific case studies cannot be given. So, just for understanding, there is a plant and the filter choking, it requires plant shutdown. So, if filter has choked, there are consequences that filter might rupture or filter efficiency comes down like. So, if you can track it, So we know these data are available on the filter because we are using data driven approach, and from there we infer our line, that is here our prediction occurs in the normal domain, upper bound, lower bound and all that, and then finally we have this line which is tracking as far as the degradation is concerned, and this is our uncertainty bounds are here, and this is our failure criteria. Okay. So predicted trend of so this is prediction trend. So before it comes here, here that failure criteria I have not mentioned explicitly here. This is the line, threshold line we call it. So this is 5%, this is 10%. So you can take a chance to go to a little conservative side, but then you have to take some action and take take the filter in this shutdown, next shutdown, or immediately, depending on the situation, the time that you have here. And this is done by having data, performing recall tests. So whatever data sets we have for training, 20% data sets are kept spared for recall test. Recall test means testing the ability of the network, and 80% data goes in building the training the network, and that's how it works. So this recall test will tell a priori whether my ANNs or PHM has been performing, and the criteria is pressure drop building into the system. So this could be a very good example for saving the plant trip, action taken before that or after that. It could be after that also. If my plant shutdown is only 10 days away, and I can get from here that okay, it is giving 12 days time, so I can take, but then unwarned or unanticipated failure will not happen in this case. Okay, so now overview is we have discussed PHM, it's a technical module, AI's role over here, and how to build a PHM, PHM program. If somebody wants to build on any mechanical component which is dealing with vibration sensing, temperature sensing, all these parameters, you can as well do it, but you should have a instrumentation to tell us these readings, vibration, temperature, current, motor current signature is very important, the oil quality for the bearing is very important thing. So the domain expert know which parameters will give us what information, and then integrated level 1 PR is required because we are going from component level to system level prognostics and health management, and here this gives us a very huge information, and uncertainty prediction module should be part of this PHM systems. These are some of the papers I have used for developing this lecture, and here the National Institute of Standards and Technology, Artificial Risk Management, it has that previous lecture, or coming lecture, that is we have been using it. So yeah, so Wikipedia, some information, existential, that is showing context of AI. If you have too many AIs, that the human will be deprived of their job, and it could have a societal consequences also. So these are something beyond scope of this lecture, but it is a reminder.